So here we have a problem that's going to be dealing with the conservation of energy. It says that Kathy is changing a tire that's on a hill that's 20 meters high. So here's our hill. And we're going to say that this hill is about 20 meters for its height. She trips and drops her spare tire, which is 10 kilograms. So here's her tire. That is 10 kilograms. And it's going to roll down the hill with an initial speed of 2 meters per second. So 2 meters per second is the initial velocity of this tire. We want to know what the speed is of the tire at the top of the next hill, which is 5 meters high. So somehow there must be another little hill after it rolls down. And we want to know at the very top of that hill, which is 5 meters in height. We want to know what its final velocity is. All right, so you may be asking yourself, well, final velocity, if we think about it, we learned about potential energy, and potential energy is mass times gravity times height. Well, that has nothing to do with velocity, so that might not help us out. We also learned about kinetic energy. Kinetic energy is 1/2 an object's mass times its velocity squared. Now we're getting somewhere because we're dealing with velocity. So, where do we go from here? Well, we know that the entire starting system of energy for the beginning part of the tire up at the top here should be equal to the final total energy at the top of this hill. And we state that through the conservation of energy, which can be written as the initial potential energy of the tire plus its initial kinetic energy should be equal to the final potential energy of the tire and the final kinetic energy of the tire. We could break that down even more using these equations if we'd like, to say that the initial potential energy, which would be using the initial height, plus the initial kinetic energy, which we'd be using the initial velocity, is going to be equal to the the final potential energy with the final height, plus the final kinetic energy using our final velocity squared. If we wanted to plug in for all these guys, we can start filling in all of our numbers that we already have. So for example, the mass of the tire is 10, gravity is 9.8 for acceleration, and the original height is 20 meters. We know that the mass again is 10 kilograms. The velocity is going to be 2 meters per second squared. We know that the final potential energy is still going to have the same mass and 9.8, and now the new height is 5 plus 1/2 the mass, which is 10, times the velocity final squared. We obviously don't know our final velocity, but we are going to solve for that. When we calculate our first potential energy initial, it comes out to 1960 joules, plus our second one is going to be 1/2 times 10, which is 5, times 2 squared, so 5 times 4 is 20. So it's going to be 20 joules. So if we really look at this, these two, this is the total energy initially. So that's going to be 1980 joules that was originally in the system. That means we're going to have the same amount of energy on the other side according to the conservation of energy. So let's keep plugging away to figure that out. The final potential energy ends up being 490 joules. Plus 1/2 times 10 is 5, so we're left with 5 velocity final squared. Make this a plus sign a little bit better for you. That's a plus. I'm going to drop down everything here to get everything on the same line. And now I'm getting closer to solving for velocity final. If I subtract 490 from both sides, I can start getting the variable I'm looking for by itself. 1980 minus 490 joules ends up giving me 1490 joules is equal to 5 times the velocity final squared. From here, I will bring my work up to the top here to save some room, but I'm going to have to divide both sides by 5 in order to get velocity final by itself. So that would end up giving me velocity final squared is equal to whatever 490 divided by 5 is, which ends up being 298. Now, is that the answer? No, not yet. Don't forget, I still have my velocity squared. So to get rid of that square, I need to take the square root. I then end up with a final velocity of something that is equal to the square root of 298, which ends up being 17.3 meters per second. So that ends up being my final answer. How did I get it? I figured out the total energy that originally was in the problem at the top of the first hill, and I set it equal to the same amount of energy that would be at the bottom. The truth is that the potential energy that was stored transferred to kinetic energy as it went down the hill. Then as it started going back up the hill again, kinetic energy started transferring back into potential energy. Not completely, but partially. Either way, the beginning energy of the system ended up being equal to the final energy of the system. And that has to do completely with the conservation of energy. Hope this helps and helps you walk through it a little bit better, and best of luck.